All right, Chemistry 111. This is a ACS final exam review. Now keep in mind that this semester we are not writing an ACS final exam. However, this is a good review for your General Chemistry 1 final exam, okay? Question number 1 deals with a little bit of nomenclature. Given a list of compounds, be able to determine which name is correct. So we have a bunch of different names here. Zinc sulfide, we got a formula. Sulfur 6-fluoride, vanadium tribromide, and titanium 3 oxide. Well, there's only one here that's correct, right? Zinc sulfide, remember that zinc is one of those transition metals that's an exception, okay? There's only ever one charge for zinc, and it's always 2+. It's like silver. Silver is always 1+, cadmium is always 2+. Those are the exceptions you need to know. So zinc sulfide is actually ZNS. There's no such thing as sulfur 6-fluoride, right? Sulfur is in group 6A, and so this compound would be called sulfur hexafluoride because it's a covalent compound. It's made out of two nonmetals, sulfur and fluorine. The next one, vanadium tribromide. Well, vanadium is a transition element. Vanadium is element number 23, and so this would be vanadium 3. Vanadium 3 bromide. All right, the only one here that's correct is the titanium 3 oxide, right? And we know that that's correct because oxide has a charge of -2, and if the titanium is 3+, what do? We swap those numbers, right, like this, so it becomes Ti2O3 for titanium 3 oxide. All right, next concept. So remember, these are questions and study topics. It's kind of all bundled together. Number 2, it says, given the formula of a compound made with a transition metal, right, that has a variable charge, like say, for example, copper, it could be copper 1 or copper 2, write the correct name. We have this compound here, TiSO42. Well, by now you should know that SO4 has a 2- charge, and that's called a sulfate. So if I have 2 of these, that means I've got a -2 charge times 2, which gives me -4. Now, -4 plus something gives me 0 because there's no charge for this formula. And so that something must be a 4. And so this is titanium 4 sulfate. All right, so be able to name a compound, an ionic compound that possesses a transition metal. All right, number 3, if you're given a formula in which the identity of one compound, or one component rather, is unknown, determine its identity from the given choices. So we have these choices. We have sodium, calcium, chromium, and tin. If you have XCl and there's only one chlorine, well, you know that chlorine is, when it's chloride, it has a -1 charge. So if we have -1 here, that means we have +1 here. And so this would be the sodium cation. Here we have -2, right? -1 times 2 gives you -2. So this must be +2. So this would be the calcium 2+. And then lastly, we have the formulas XCl3. We have -1 times 3. That gives us -3. So our cation must have a 3+ charge. So that means that this would be chromium 3+. All right, so there we go. We've identified the cations. Number 4, given a list of ionic compounds, determine which would have the lowest melting point. Use Coulomb's law in a qualitative way to get the answer. So qualitative means we're not going to do any major, calculations here. We know that Coulomb's law, the energy of attraction, the electrostatic force that attracts the cation and the anion, is proportional to the product of their charges divided by the distance between the nuclei. Okay, the distance between the nuclei, or R. Well, if you look at strontium chloride and strontium iodide, well, both of those have strontium, which is an alkaline earth, and both of these have a +2 charge, right? +2 and a -1, +2 and a -1 for the chloride and the iodide. Well, that means you have -2 overall for your numerator. However, if you have sodium chloride and sodium iodide, then you have +1 and -1, +1 and -1, like that. Okay, so that means we can eliminate the first 2 because +1 times -1 is only -2, which is half that of -2. And so for R, we go for the largest internuclear distance, right? Because we're looking for the one that's going to have the lowest melting point. So we want to have the weakest attraction. We're looking for the lowest possible E. So if we're looking for the lowest possible E, when you're comparing fluorine, chlorine, bromine, and iodine, right, remember that size increases. Okay, we'll put here, we'll put larger down here. So iodine is bigger than, or iodide is bigger than chloride. And so since its radius is bigger, what's that going to do? It's going to cause this to drop even more. And so out of all of these, sodium iodide is going to have the lowest melting point, right? It's going to take the least amount of energy to pry or to break the electrostatic attraction between the sodium cations and the iodide anions. Question number 5, if you're given a list of compounds, determine which one has covalent bonds. If it has a metal or a transition metal, it's ionic, so discard that. If we look at these compounds here, we have titanium 2 oxide, then we have lead 2 chloride, we have barium iodide, then we have carbon diselenide. Now I know we didn't look at a lot of diselenides here, but could anybody tell me which one of these possesses only nonmetals? Would it be 1, 2, 3, or 4? It's not a trick question. Thanks, Anthony. Absolutely. Right? Titanium, oops, wasn't the highlighter. Titanium, palladium, and barium are all metals, right? Therefore, all 3 of these are ionic. If you look over in the P block and look under oxygen, you see oxygen, sulfur, and below sulfur is selenium. So everything here is a nonmetal. Carbon is a nonmetal, and selenium is a nonmetal. In fact, if you were to draw a Lewis structure, it would look just like this, right? Now that's neither here nor there. I'm not asking you to do that right now, but this is a covalent compound. All right, recognize what an isotope is, right? So if you need a little bit of reviews on an isotope, remember that the number of protons is what governs the identity of an atom. However, even if we have elements that have the same number of protons, the number of neutrons can vary, and when they do, we get different isotopes. Say, for example, if you have carbon-14 and carbon-13, these two here, these are common enough isotopes. Carbon-14 is used for carbon dating. Well, if we compare these two, you have carbon-14, carbon has 6 protons, and if you compare it to carbon-13, right, remember that this number here, this is the mass number, which is the sum of the number of neutrons and protons. And so carbon-14 has 8 neutrons and it has 6 protons, whereas carbon-13 has 7 neutrons and it still has the 6 protons. All right, so that's the kind of rationale you want to take there. So carbon-14 and carbon-13 are isotopes. Carbon-14 and nitrogen-14 rather, they are not isotopes. Right? They're 2 different elements. They have different numbers of protons. Carbon has 6 protons and nitrogen has 7 protons. If we look at the next one, nitrogen-14 and nitrogen-14 with a 3- charge, well, that only differs in the number of electrons. Right? They are not isotopes. They do not differ in the number of isotopes. Here we have an element and a compound. Right? This is carbon-12 in carbon monoxide. So those are completely different. Then we have nitrogen-14 and then nitrogen-14 in a nitrogen molecule. And so those are not isotopes of each other. So carbon-14 and carbon-13 are isotopes. And you need to know the difference between mass number and, of course, atomic number, which is the number of protons. All right, let's try a problem that involves a little bit of math here. It says, given a mass percent abundance of one isotope and the mass percent abundance of a second isotope, determine the mass of the second isotope. Bromine is a naturally occurring mixture of 2 isotopes. One isotope has a mass of 79 atomic mass units, has this relative abundance. And what is the mass of the second isotope if its relative abundance is 49.31? Well, you can see that we only have 2 sig figs here, so we should only have 2 sig figs in our final answer. But we did look at problems like this at the beginning of the class. Right, if you go to the periodic table right now and you look at bromine. Bromine is element number 35. What does it say for the molar mass? It should say 79.90 atomic mass units. Okay, and if you want to write grams per mole, that's fine. It's going to give you the exact same answer. Well, bromine has 2 isotopes, right? Isotope 1 and isotope 2. So 50.69% of the time, or 0.5069 out of 1 of the time, and I'm just expressing this as a fraction out of 1, so 0.5069 out of 1 of our isotopes has a mass of, what, 79? Yes, 79 atomic mass units, like that. Whereas the second isotope that we're looking for the mass of has a relative abundance of 0.4931 out of 1. All I'm doing is taking these numbers and dividing by 100, right? And if you want to put them in as 49.31 over 100, well, whatever, gives you the same thing, times the mass of the other isotope. So now all we have to do is solve for x. And when we do that, and I'm going to skip all the algebra, I'm assuming that you know how to solve for x at this point. When we solve for x, we get that x is equal to 80.82 AMU. Now again, we were only given 2 sig figs for the other atomic mass, so this would roughly equal 81 atomic mass units. And that makes sense because just from, a little bit of knowledge of the periodic table, I know that the 2 isotopes of bromine are bromine 79 and bromine 81, and they have a relative abundance of about 1:1. That's important. If you're the kind of person who's into those crime shows at all, sometimes you'll hear them talk about mass spectrometry. So mass spectrometry, not mass spectroscopy, but mass spectrometry. In mass spectrometry, this is one of the rules that they use to determine whether a drug or a molecule contains bromine, is they'll analyze it and they'll look for the isotope of bromine, and if they have a roughly 1:1 abundance of the 2 isotopes, they know that it's bromine. Anyhow, kind of interesting there. Question number 8, calculate the protons, neutrons, and electrons in an ion, right? How do we know the number of protons in an ion or an atom? They're given by the identity of the ion. You go to the periodic table, you look up any element, molybdenum, it's element number 42. It's got 42 protons in the nucleus. How do we find neutrons? Well, I said that we take the mass number, we subtract the number of protons, and that gives us the number of neutrons. Electrons are found by, if you have a negative exponent, remember that electrons are negative. Sometimes students will get confused with that and they'll say, well, if it's negative, maybe I should subtract them. No, if you're trying to determine the number of electrons, and let's say you have a 3 minus charge, you would add 3 more, right, to it. Let's take a look at an example here. It says, give the number of protons, neutrons, and electrons in calcium, a calcium 40 2+ ion. So let's write out the whole atomic symbol here. We have calcium. It's got a 2+ charge. It's calcium 40. If we go to the periodic table, we see that calcium is element number 20. So what does that tell us? We're looking for the number of protons, neutrons, and electrons, right, in this isotope and with this charge. Well, we know the number of protons is going to be 20 because that's given from our atomic number. How do we determine the number of neutrons? It's going to be equal to 40, which is the mass number, the sum of neutrons and protons, subtract 20, which was the number of protons, and we get 20 there as well. Now, if the calcium had no charge, it would have 20 electrons, wouldn't it? But if it's got a 2 positive charge, that means you lost 2 electrons, because electrons are negative, right? If you lose something negative, you become positive. And so we have a total of 18 electrons. And so the answer would be 20, 20, and 18. All right, let's just discuss number 9. It says conceptual understanding of the relationship between empirical formula and molecular formula. Having the same molecular formula, or empirical formula rather, does not mean you have the same compound, right? Let's say I give you the question to solve for an empirical formula, and you figure out that it's CH2O. Well, does that mean that it's, CH2O, the only way you can put those together would be to make formaldehyde. But what if that's just an empirical formula? What if you multiply this whole thing by 6, you get C6H12O6, which you probably recognize as being the molecular formula for glucose, okay? Acetic acid also has the same empirical formula as formaldehyde, which is CH2O. So you can't just take a look at an empirical formula and know that you've got the molecular formula. You have to figure that out. All right, there we go. Given an element, determine which is more similar to it. It's asking us here, which one of these is more chemically similar to magnesium? Well, hopefully you remember that when we're talking about resemblance between elements, right, chemically similar, we're going to be talking about groups, okay? Group or family. Because remember that just like people who are in the same family may resemble one another, elements that are in the same group or the same family, which are the vertical columns, will resemble each other. If you look at group 2A, you have beryllium, magnesium, calcium, strontium, barium, radium. Well, you see here that calcium is in that group. It's in that family, and so it's going to closely resemble magnesium, right? You know that when magnesium forms an ion, it always forms a magnesium 2+, because if it loses 2 electrons, it becomes isoelectronic with a noble gas, neon. Whereas calcium likes to lose 2 electrons because then it will become isoelectronic with another noble gas, argon. So that's the kind of thought process you want to have. Given the mass of an ionic compound, determine the number of ions of one of its individual components. If you have 34.5 grams of sodium azide, or sodium nitride rather, how many sodium ions are present? Well, let's see if we can solve this by dimensional analysis. I realize there's not a ton of room on here, but I think we can do it. If we have 34.5 grams of sodium, sodium nitride, and I've gone ahead and looked up the molar mass of sodium nitride already. So Na3N rather. So the sodium nitride, I'm getting mixed up with sodium azide, which is something completely different. Anyhow, sodium nitride has a molar mass of 82.98 grams per mole. So we can use that in order for us to determine the number of moles of sodium nitride. So we have 82.98 grams in 1 mole. Well, we know that in 1 mole of sodium nitride, we have 3 moles of sodium ions. Right now, if we were to stop right here, we have the grams canceling the number of moles of sodium nitride. If we were to stop right here, all we would have is the number of moles of sodium, but we want to know the exact number of ions. So luckily, we know that in 1 mole of sodium ions, we have 6.022 times 10 to the 23rd power ions of sodium, right? That's a total number. And I could have put Na+, but whatever. There we go. So when we punch all that spinach into our calculator, I've gone ahead and done this already. We should have a really big number, shouldn't we? I have 7.51 times 10 to the 23rd power sodium plus ions, right? It's a huge number. Okay. It's a huge number. Absolutely it is. Does it make sense? Yeah, it totally makes sense that we would have a big number of sodium ions because we have 34.5 grams. Okay, number 12. Given identical masses of 4 elements, determine which one has the least number of atoms. The higher the molar mass, the smaller the number of atoms present. Given 15 grams of each of the following, which one would have the least number of atoms? So let's say you have 15 grams of carbon, right? 15 grams of neon, 15 grams of beryllium, and 15 grams of oxygen. If we look at the molar mass of carbon, it's about 12 grams per mole. If you look at the molar mass of neon, it's about 20 grams per mole. If you look at the molar mass of beryllium, it's about 9 grams per mole. And these are just roughly. And then oxygen is around 16 grams per mole. Well, let's think about that. If in 1 mole of each of these, you have all the way from 9 to 20 grams, right? That means the one with the highest molar mass, when you have 15 grams of it, it's going to have the lowest number or the smallest number of atoms, won't it? Right? You have the same mass of each one of them, right? But since these are heavier, to get up to 15 grams, you don't have to count as many atoms out. And so this is just a conceptual question. Give me a thumbs up if you follow me on that one. This is a question where no math is required. It's just more an understanding that different atoms have different molar masses. That's all. And they mean something. There's a consequence to it, right? It's like the question I asked you in one of the post-lab questions. I said something of the ilk, and I don't remember it, verbatim, but it was something like, what weighs more, a mole of marshmallows or a mole of carbon? Well, a mole of carbon only weighs 12 grams. A mole of marshmallows, I don't even want to think about how much that weighs. That weighs more than the earth, for all I know. It weighs a lot, okay? They say if you had a mole of oranges, it would cover the surface of the entire planet of the Earth. In the thickness would be something like a mile thick of oranges, or maybe more than that. So a mole is a huge number. Okay, number 13. Given a compound and a number of molecules, determine the mass of one of its individual components. What is the mass of phosphorus atoms present in this many molecules of diphosphorus monoxide? Okay, let's see if we can solve this one here in the provided space. We're starting out with 7.45 times 10 to the 22 molecules. I'll put molecules of P2O. But we know in a mole, 6.022, we know that in 1 mole of P2O, we have 6.022 times 10 to the 23rd power molecules of P2O. If we were to stop right here, all we've done is canceled out molecules of P2O, and we would have the number of moles of P2O. But remember, we're trying to figure out what's the mass of the phosphorus atom. So we want that in grams. So now that we have the number of moles of P2O, we can take and say, well, in 1 mole of P2O, we have 2 moles of P, right? 2 moles of phosphorus. We know that in 1 mole of phosphorus, going over to my periodic table, looking at element number 15, we have 30.97 grams of phosphorus. Look at this. It's not magic. Moles of P2O cancel, moles of phosphorus cancel, and we're left over with the mass of phosphorus, which is 7.66 grams of phosphorus. All right, and the answer should have 3 sig figs because our number of molecules of P2O had 3 sig figs. Question 14, if you're given the formula of a compound, determine the mass percent of one of its individual components. I'm not going to spend a lot of time on this one. This is a question that students usually get pretty quickly. It's asking us, what's the percent of manganese? Remember the Mn is manganese, Mg is magnesium. They're 2 different things, manganese, magnesium, right? Sometimes students might get confused in that. But look, if we have this giant compound here, GaMn2O7, and there's 3 of them, right? Okay, well, we get this big compound here, this big ionic compound. Well, I want to know the percent mass of manganese in that entire compound. Now, I've gone ahead, and I think that all I did was look up the molar mass of this, and I might ask you to calculate the molar mass of something crazy like this. It's 805.06 grams per mole. So it's heavy, right? It's a big ionic compound. Well, if in my denominator, I have my molar mass, 805.06 grams per mole, and I'm looking for the percent of manganese. Could anybody tell me how many manganese atoms there are in this formula, in 1 formula unit of this? And it's not a trick. Mr. Dion hates trick questions. Yeah, it's 6, exactly, because I have 2 times 3, and 2 times 3 is 6. Excellent. So I have 6 times the mass of a manganese. In a manganese, go over to your periodic table. Manganese is element number 25. It's 54.94 grams per mole. Okay, so I put that in my numerator. I have the entire formula mass in my denominator. Multiply that by 100%. You see that the units of grams per mole cancel. I should end up with percent, which is unitless, unless you count percent as a unit, and you get 40.9% manganese in that compound. All right, let's take a look at another concept here. It says, given a hypothetical compounds ratio, and I think it means ratio of elements, determine the mass percent of one of the components. So let's say you have a compound that has a ratio of 1 carbon for every 3 hydrogens. What's the mass percent of carbon? Well, the mass percent of carbon is going to be equal to the mass of carbon divided by the total mass, okay, multiplied by 100%. So if we have 1 carbon weighs 12.01 grams. And if we have 1 carbon for every 3 hydrogens, so we have a carbon in the denominator plus 3 hydrogens, 3 times, 3, come on, times 1.01 grams per mole, and I'm just leaving out the moles here. And when we do that, we end up with 79.9 is what it should be, percent, because I only have 3 sig figs because I've only used 3 sig figs for the mass of the hydrogen. There we go. So mass percentage of a compound in an empirical formula. So there we go. Oh, here we go. Into the structure of the atom, right? We started out by looking at electromagnetic radiation. We talked about infrared and UV and X-rays and all that good stuff. All right. There we go. So it says, what's the energy of this photon? Well, what are some formulas that you would need here to calculate the energy of a photon when you're given wavelength, right? Lambda represents wavelength. Well, you know that the speed of light, which is in meters per second, right, is equal to wavelength, which is in meters, times frequency, which is in seconds to the -1, or hertz. Either way is fine. And we also know the formula that E is equal to h, Planck's constant, multiplied by frequency. So if we rearrange this formula, if we rearrange this to be frequency is equal to c over lambda, from there we can plug this into the frequency unit here, and we get E is equal to h times c divided by wavelength. We know Planck's constant, we have the speed of light, we have the wavelength, and we can calculate the energy. But we need to convert the wavelength into meters in order for the units to work out to give us joules. So let's try plugging in some numbers here. We have E is equal to h times c over lambda. I'm given 3 sig figs here, so 3 sig figs for my speed of light will be fine. 6.626 times 10 to the negative 34 joules times seconds, multiplied by the speed of light, 3.00 times 10 to the 8th power meters per second. And then my lambda, it's going to be 732 times 10 to the -9 meters. Right? You should know that in 1 nanometer, we have 10 to the -9 meters, right? That's a conversion factor, nano, right? They're very small, so it's 10 to the power of -9. There we go. You can see that, you can see that meters cancel, seconds cancel, and I'm left over with the units of joules. So when you punch all that spinach into your calculator, you end up with 2.71 times 10 to the -19 joules as being your final answer. There it is. 17, conceptual understanding of relationship between energy and quantum numbers in multi-electron systems. In English, what do the quantum numbers really tell us about the atom? Well, let's just go over this kind of quickly. So n is the principal quantum number. So I'll just, I'm pretty slow at writing here. So principal quantum number, and I can promise you that quantum numbers are going to come up on the final exam. The principal quantum number is most closely related to the size, right? As n increases in a period, so does the size of the atoms as the shells get bigger. L is the angular momentum quantum number, so angular momentum quantum number, and that's related to the shape. Right, you remember when L is equal to 0, 1, 2, 3, we have S, P, D, F, and all of these different types of orbitals have different shapes, don't they? An S is a sphere, a P is a peanut, D, those get kind of wacky. A lot of them look like a 4-leaf clover, except for the DZ squared, which looks like a donut around a P orbital, and then F, those are just crazy, okay? ML is the magnetic orientation, or the magnetic quantum number, so we'll put here magnetic quantum number, which describes the orientation. Right, if you have an L of 1, let's say, ML can be -1, 0, and +1, because a p orbital, there's 3 types of p orbitals, so we went over that. And then MS, usually students have that one down. This is the electron spin. And so that just indicates the direction of spin as being up or down, which is sometimes called an alpha or a beta spin state, but we can just use up or down. It's totally fine in this class. All right, number 18. This is a real chestnut, a real classic in General Chemistry 1. if you look at a whole bunch of different quantum numbers, just determine which one is wacky. Is there any one that stands out to you guys immediately? What does it say? Which isn't allowed. Okay, I was going to say now, once I looked at it, I'm like, oh, I think there's more than one here that isn't cogent. So could anybody tell me which one of these is, which is an allowed set of quantum numbers for a 5D electron in the ground state of Mercury? I should read the whole question before answering it, shouldn't I? So I'm looking for an allowed quantum for 5D electron in the ground state of Mercury. Well, if it's a 5D, right, we have our quantum numbers N, L, ML, and MS. If it's 5D, then N is 5, L is 2, okay? And if it's in the ground state, that means it's not excited. If you look at these two, those aren't right because those represent F orbitals. There's a major problem with this one. We have a -3 here. ML can only be, the lowest it could be is -2, so that's not right. So here's the only possible answer. It's 5, 2, +2, and +0.5. So this would be our ML value. And then here we have our MS value. Kind of a weird question, but makes sense. Yeah, you know, I'll just tell you guys what I was looking for from this question, and I think the way that I asked it on the exam was, I give you a list of quantum numbers and tell me which one is not allowed, right? So you just have to know the rules, right? You know what the values of L are, and then you know that ML, for example, is equal to -L all the way up to 0, all the way up to +L, and the MS can be +0.5, or it can be -0.5, right? That's the kind of stuff you need to know, right? And then, of course, L is equal to 0 all the way up to N-1, right? That's the kind of things that you have to know, okay? And we've looked at plenty of questions like that earlier on when we talked about electronics or atomic structure. Question number 19, determine the ground state electron configuration of transition metal ions. What's the electron configuration for molybdenum with a 2+ charge? Well, molybdenum is element number 42. So let's start with just molybdenum, okay? If we look at just good old molybdenum, what's the noble gas that precedes molybdenum? It's krypton. So we have, I don't know why I put square brackets around this. There we go. So we have molybdenum, which is krypton. What comes after krypton? We have 5s2, and then we have a 4d, 1, 2, 3, 4. So 5s2, 4d4, like that. Now, remember that this is one of the exceptions, isn't it? Because molybdenum is right below chromium. And chromium and copper, I went over those exceptions. And so it's actually not 5s2, 4d4. It's 5s1, 4d5. Why? Because now both of the s orbital and the d orbital are half filled. And so there's additional stability in having both of those orbitals half filled. So now that this is our electron configuration of molybdenum, now we need to remove 2 electrons, right? If we remove 2 electrons to make molybdenum 2+, we're going to have krypton. The electron that we're going to remove first would be the 5s1 electron. Remember the first in and first out rule. So we take out the 5s electron first, and then we have to take one of the 4ds, and we're left over with 4d4, like that. So that would be the electron configuration for molybdenum with a 2+ charge. Question 20, given an orbital filling diagram like this beauty right here, determine the identity of the atom. Which ground state atom has the electron configuration described by this orbital diagram? So let's write down what we got. We got argon, right? Argon is element number 18, so this is something in the 4th period. Then we have 4s2, 3d10. 3d10 takes us all the way to zinc. Now we're back into the p block. And then we have 4p4, right? There's a total of 4 electrons here. So if we go from the 4p block, we have gallium, germanium, arsenic, and then what? Selenium. So this is selenium. Number 21, given a periodic trend, determine why it happens that way. Why does atomic radius increase going down and to the left? Well, it's a twofold reason, isn't it? It's because the principal quantum number increases, so N increases. That's one thing. And it says down and to the left. It's because effective nuclear charge decreases, or we have a lower effective nuclear charge, ZF. And I'm not going to ask you about really an explanation, I don't think, of the periodic trends. It's more that you're able to apply them. Why does electronegativity increase going up and to the right? It's just because of increased effective nuclear charge. So increased effective nuclear charge. Also, the atomic radii gets smaller, so smaller atoms. Put that as smaller atoms. Remember effective nuclear charge. So we went over that in detail, and I explained why as you go across a period from left to right, that the number of protons in the nucleus increases, but the number of shielding electrons or core electrons or inner electrons remains the same. And so as you're adding more and more protons, you're getting more and more positive charge in that nucleus as you go across a period, but the number of shielding electrons that are blocking that positive charge from the outer electrons is staying the same. So as the positive charge increases and increases, it's going to pull the outer electrons or the valence electrons in closer and closer and closer, which is counterintuitive, but that's the way effective nuclear charge works. Given a list of atoms in number 22, determine which has the highest specified periodic property, which one's going to have the highest effective nuclear charge. Well, what do we have here? We have arsenic, selenium, and we have strontium and barium. Well, strontium and barium are in group 2A, so they're not even in the running, right? They're in group 2A. They're way over on the left-hand side of the periodic table. Then if we compare arsenic and selenium are both in period 4. So they're both in period 4. However, arsenic is in group 5A. So this is in group 5A, and this is in group 6A. And so selenium will have the highest of the effective nuclear charges amongst these 4 atoms. Which ion has the largest radius? So we're looking for the biggest one. Remember that when you have a cation, cations are smaller than a neutral atom. Why? It's related to effective nuclear charge. Think about it. If you have potassium, right, just good old potassium, you get 19 protons, 19 electrons. Well, you have 18 shielding or inner core electrons, and you have the 19 protons in the nucleus. If you remove the electron, the valence electron, well, then all of that nuclear charge is going to be pulling in on the core electron. So there's more positive charge per electron that's left over. So that's why cations, the more highly charged they are, the smaller they get. So when you go from potassium to calcium, calcium is smaller, right? And potassium, shit, I didn't mean to do that. I mean, a calcium 2 plus is smaller, okay, than a potassium ion, which is larger, okay? But then if we compare sulfide and chloride, both of those are isoelectronic with argon, aren't they? Okay, both, we'll put here both have 18 electrons. Well, again, you can use effective nuclear charge as one way to explaining that the sulfide would be bigger than a chloride. But I've taught the class long enough to know that I think an easier way for students to remember it, and there's nothing wrong with this, is let's think about it. If you've got extra electrons, you've got 1 extra electron here, and you've got 2 extra electrons here. The more extra electrons you have, the more electron-electron repulsion there's going to be, and the more space they're going to want to take up. And so sulfide is going to be bigger than a chloride. All right, ionization energy. Question C, which atom has the largest ionization energy? First ionization energy. What's ionization energy? It's the amount of energy required to remove an electron from an atom in the gaseous phase, right? You have an atom in the gaseous phase. You make the cation in the gaseous phase, plus you've lost an electron. Well, the amount of energy that it took to do that is called the ionization energy, which is usually measured in kilojoules per mole. We have a calcium, we have a carbon, we have an oxygen, and we have a beryllium. Well, calcium's definitely going to have the lowest, right? Calcium is way over on the left-hand side of the periodic table. It's a metal, group 2A metal. Those like to lose electrons, right? It's a big element. If we go over to a carbon is much smaller than a calcium, both because of principal quantum number and because it's further to the right in the periodic table. So it's going to take more energy to remove an electron from a carbon. But if we go from carbon to oxygen, oxygen is even smaller than carbon, right? It's got an increased effective nuclear charge. And so it's going to take even more energy to remove an electron from oxygen than it would from carbon. Now, I kind of left beryllium out here, but hopefully if you understand the rationale as to why the first ionization energy of oxygen would be higher than carbon, well, beryllium is even behind those, right? Beryllium is way back in group 2A. Beryllium is a pretty big element for being in, period 2, and so it's being in group 2 of period 2, and so it's easy to remove an electron from beryllium. Okay, so make sure you know these types of trends. This is a real chestnut, this one here. If you're given a list of successive ionization energies, you should be able to determine the identity of the element. Let me show you what I mean. It says, which period 3 element has these successive first through sixth ionization energies? Look, we got ionization energy 1, then you go to 2, it looks like it's about 3 times as much. You don't even double it here. Then all of a sudden you get jacked up to from 2,700 up to 11,500. That's a big jump, right? You can see that there's a big jump going from these 3 numbers to this number and then the subsequent numbers. So that tells us that we have 3 valence electrons in this atom. Okay? And they tell us that it's in period 3. Go to period 3. You go sodium, magnesium, and then aluminum. Therefore, this must be an aluminum. 3 valence electrons, and it's in period 3. Number 24, given a formula, determine the number of lone pairs on the central atom. How many non-bonding electrons are in the central atom of ICl3? So let's tally it up here. If we have, son of a gun highlighter, no way. If I have ICl3, all of these are halogens. Iodine has 7. Chlorine has 7 valence electrons times 3. That's 21 plus 7, which gives us 28 valence electrons. Now, most of the time, chloride is going to have 1 bond and 3 lone pairs. Okay, iodine here is less electronegative. It's going to be the central atom. So far, we've used up 8, 16, 24 valence electrons. So that means that we've got 28 minus 24, which leaves us 4 left over. Where are they going to go? They're going to go on the central atom. 2 here and 2 here. So there's 2 lone pairs on the central atom. So that means we have a total of, I'll write it in black ink, I guess. We have 4 non-bonding electrons on the iodine in ICl3. So make sure you know how to draw a Lewis structure. What is the formal charge on selenium in this molecule? It's kind of a funky molecule here. I'll just write it out a little bit bigger. We have silicon. Oops, what happened there? We have silicon with a triple bond to selenium. Okay, we got a lone pair on the selenium, and we've got a lone pair on the silicon like that. And we're asked to determine the formal charge on the selenium. Well, if we go to our periodic table, which of course you're going to have, selenium is in group 6A. It has 6 valence electrons. You see oxygen, then sulfur, and then selenium is next. 6 valence electrons. Remember that when we're calculating formal charge, we subtract the number of sticks and the number of dots. So we have 6, subtract 3 sticks, subtract 2 dots gives us positive 1. Therefore, we have a +1 charge on our selenium, like that. All right, let's move on from there. Conceptual understanding of resonance structures. So if you're unsure about the concept of resonance structures, an example that comes to my mind of something that we looked at would have been the resonance structures, I believe, of carbonate, the carbonate ion. So if you need to go in the textbook and look at resonance structures, which, resonance structures are nothing more than we want to draw a Lewis structure of a molecule, and we can't draw any one perfect Lewis structure that perfectly sums up the electron distribution in our Lewis structure. And so we have to draw a collection of structures which shows how the electrons are delocalized, or they are present in more than one sort of area of our polyatomic ion or of our molecule, whatever. All right, conceptual understanding of bond length and bond strength, right? If you have bonds and you're comparing them in terms of strength, the triple bond is the strongest, double bond is intermediate, and then single bond is the weakest. If you're talking about bond length, the single bond, or maybe I'll use a different color, single bond is the longest, followed by the double, and then the triple is the shortest, and that's just because of the more orbital overlap you have, the closer the elements have to get to one another. What's the shape of the Brcl4 plus ion? Remember, you won't have the Vesper handout. Remember how I gave you the handout with the reds for exam 5? That was like a training wheels, right? You don't get that for the final exam. Let's take a look at this Brcl4 plus ion. Just give me a sec here. All right, there's some other work we did. We have Brcl4 plus. Well, bromine has 7 valence electrons. Chlorine has 7 valence electrons. We have 4, so that's 28 plus 7. And then since we have a negative charge, we're going to subtract 1. So we have a total of 34 valence electrons. We're going to put the least electronegative element in the center like this. We get the bromine. We'll just draw some bonds to chlorine like this, 1, 2, 3, 4. Normally the halogens, fluorine, chlorine, bromine, and iron, not all the time. You can see it's not always true, but a lot of the time the terminal atoms will have 1 bond and 3 lone pairs. So let's put all those in here. And once we've done that, we've used up a total of 32 valence electrons. So subtract 32 valence electrons. That gives us 2 electrons left over, which we would have to put on our central atom like that. So that is our Lewis structure for this molecule. Now, I don't know if there's enough room for me to put it on the review handout here. Where was I? Oops. No, I was somewhere around here. Let's see if I can squeeze it in here. The land of the free for 2-3 more weeks. There we go. Now, what other questions are they asking us? Oh, that's a crazy stuff. Okay. I need a new prescription so bad, and every time I look at something, close up, I'm just all I can barely see the lone pairs or the unpaired electrons. Anyhow, what is the shape of Brcl4 plus? Well, if you have 5 regions of electron density, right, they adopt a trigonal bipyramidal electron geometry, but then when you remove one group, shoot, I should have drawn it the right way. Anyhow, then you end up with something. I'm going to see if you guys can name it. I'll just draw it. I don't have the solutions, but I have them on my computer. Can you guys name this? Molecular geometry. I know I'm doing a lot of talking. It's hard to pay attention when your instructor's doing nothing but jibber jabber. Yeah, thanks, Anthony. Absolutely. It's the seesaw. Seesaw. Did you see saw? Yes, I saw saw. So seesaw. Another name for that is the distorted tetrahedron, is what our book calls it, I think. Distorted tetrahedron. But if you're the kind of person who likes to look up things on YouTube and stuff, I'm sure you've seen seesaw show up from time to time. Given a list of 4 molecules in 29, determine the one with the tetrahedral shape around the central atom. Oh, jeepers. We're going to need more space to draw all of these molecules. So let me go back here. Give me 2 seconds. And let's practice our Lewis structures. There we go. So we've got radon tetrachloride. So we'll start with RnCl4. Radon is a noble gas. It's got 8 valence electrons plus 7 times 4. So that's 28 plus 8, which gives me 36. 36 valence electrons like that. If I have my radon. Anyhow, I put the chlorines around like this. I think I'm getting tired. Starting to get silly. So if I put the chlorines all around it like this, and I'm kind of tallying it up in my mind. Here we have 8. We have 8 times 4, so that gives us a total of 32 electrons that we've used up. So 36 subtract 32 electrons gives us 4. So that means we'll put up 1 here and 1 down here. What was the question? Which one of them is tetrahedral? Yeah. So this one is square planar. Square planar. What's the next one? Is it sulfur tetrafluoride or sulfur hexafluoride? Good gravy. I have a big screen here that my brother-in-law gave me. I'm going to bring it up on that. It is sulfur tetrafluoride. All right. So we have SF4. So we have 6 valence electrons here, plus 7 times 4, which is 28 plus 6. So that's 34 valence electrons. So again, I'm kind of doing this one in my head as I go along here. So we'd have one, put this guy in the back like this. Put this one over here, this one down here. Complete all of the octets of the fluorines. So that's 8 times 4, which is 32. And then I have 2 left over, so those are going to go here. Here we go, right, Anthony? This is the seesaw. You were the one who identified that the last time. What's next? Silicon tetrachloride. So SiCl4. So that's 4 plus 7 times 4. So 4 plus 28, which gives you 32. So we have silicon. This one's, nothing's easy in chemistry, is it? But some things are more abundantly clear than others, right? If we have 8 electrons on each of these, between the chlorines and the bonds, this would give us 32 electrons. So this one is going to have bond angles of 109.5 degrees. And it's, the answer is silicon tetrachloride would be tetrahedral. And the last one is phosphorus tetrachloride. I'll just not skip it, but I'll help you with it in case you want to practice. PCl4. Okay, we have 5 valence electrons plus 7 times 4. Did I write it then? Yeah, it must have a positive charge. That's not right. Let me go back here. That must be a typo. Because otherwise you'd have a radical, and there's no way I would ask that. Not on that. Not on that. That's way too complicated. Yeah, that's a typo. That should say PCl4 plus. Okay, it should be a cation, because then it gives you a seesaw, or the distorted tetrahedron. It looks like this. All right, that's kind of a lengthy problem, isn't it? Where you have to solve a bunch of Lewis structures. I'm going a little slow, I think. Okay, you have the seesaw. So the answer was the silicon tetrachloride. You know what? If you're ever in a crunch for time in an exam, and I was the kind of student, I mean, I didn't run into time very often, but if I ever did, sometimes if I was asked a question like this, I'd look for something that looked like something I knew. So I'll give an example of how I would have solved this in my second year university, you know, if I was crunched for time. Because I didn't know what the molecular geometries of all these were. I didn't have any stuff memorized like I do now. I mean, I teach chemistry for a living. Anyhow, so here's the positive charge on the sulfur, by the way. But I know that carbon tetrachloride, like that's something I had memorized from organic chemistry, that is tetrahedral. And silicon is in the same family as carbon. So, you know, you can kind of piece it together like that. Anyhow, just kind of little tricks you'll learn along the way. Fun stuff. Given a structure, would checking for divisibility by 8 to eliminate? Sure, absolutely. You can do that. Anthony, whatever tricks work for you, like tricks are something that I don't like to develop while I'm writing the exam, but you know, any tricks that you can develop ahead of time, I think is never a bad idea, you know, never a bad idea. Oh, I see what you're saying. So since you have halogens on all the extremities, you make a multiple of are you talking about the lone pair on the PCl4 plus?
Yeah, just in general, I was looking at it as if you kind of divided it by 8, or you had to get the multiple 8, you know, you get to 32 because each of these have a 4.
Oh, I see what I did wrong. Yeah.
And then so
if you
get extra ones, you'd have a lone pair. Therefore, you'd have something that would have 5 instead of 4.
Yeah. So, Jiang, to answer your question, I knew it was an ion. I just drew a cation when it's an anion, right? That's my mistake. There we go. I'll have to go back and fix that. So phosphorus has 5 valence electrons. Subtract 4 bonds and 2 dots, right? There you go. That makes much more sense. All right, good. All right, boom. There we go. Problem solved. Anyhow, let's see what's next. Number 30. Given a structure, use VSEPR, valence shell electron pair repulsion theory, to determine bond angles on different elements. What are the bond angles on carbon 1 and carbon 2? I'm not going to go over this in a ton of detail because this is the kind of thing I could lecture on for the next 20 minutes, really. But carbon 1 has 4 single bonds, right? When carbon has 4 single bonds, if you look at the electron configuration, here I go, doing something I said I wouldn't do. A 2s2, 2p2, right? You have the 2s electrons that are paired up, and then in the 3p orbitals, you have 1, 2 electrons. So what do you have to do? You have to hybridize them to make 1, 2, 3, 4 sp3 hybrid orbitals where they each have 1 bond like that. So this is sp3 hybridized. If it's sp3 hybridized, that means it's tetrahedral. You've got 4 bonds, no lone pairs. The bond angles are all 109.5 degrees. Now, if I delete this stuff here, the second carbon on carbon 2 has 3 sigma bonds, but it's got a pi bond, doesn't it? So that tells you, and I'm going to skip the whole lesson in hybridization, that it has 3 unpaired electrons in sp2 hybridized orbitals. Then it's got an unpaired electron in the 2p orbital. So since it has 3 regions of electron density, the double bond and the 2 single bonds, that means that not only is it sp2 hybridized, but the bond angles are going to be 120 degrees. Okay, so this is kind of just a, question about hybridization and bond angles, stuff that we looked at quite a bit. Number 31, given a series of formulas, determine which molecule does not have planar geometry. You got the phosphite ion. Look for lone pairs on the central atom. This is a trick. This one here, which does not have a planar geometry. Okay, so this is a shortcut. And it wasn't me who wrote this. This is a Dr. McCumber thing, and she's not wrong. But if you look at that handout that I gave you for exam 5 with the regions of electron density and the molecular geometries, which I told you was like the training wheels, usually when you have lone pairs on a molecule, on a central atom, most of the time it's not going to be planar. Are there exceptions? Yeah. Okay, we even looked at an exception this evening, right? But most of the time, I'd say when you have a lone pair in the central atom, it's not planar. Okay, again, not all the time, but most of the time. When I teach nursing chemistry, for example, we don't look at shapes like the octahedron. We don't look at the trigonal bipyramid at all. We stop at the tetrahedron. So in nursing chemistry, one of the shortcuts that I teach them is I'll tell them, if you have a lone pair on your central atom, it's almost always going to be a polar molecule, okay? And that's, I still teach them the whole concept of Lewis structures, but just a little helping hand there. Anyhow, in the interest of time, I'm just going to show you if we have the phosphite ion, that's, I can't see anything. If we have a phosphite ion, that's PO3 minus. So PO3 minus 1. So that's going to look like this. Then we're going to have another oxygen here, another oxygen here. And I've gone over quite a few Lewis structures this evening, so I'll cut this one a little short. So that is planar, right? That's trigonal planar, and you could draw the resonance structures for that one. If you have nitrogen trifluoride, that's going to be trigonal pyramidal. I'm going to leave the lone pairs out just in the interest of time, and so that must be the answer. We can still do the other ones just for fun. If you have silicon hydride, so this one here, Si2H2, that's going to look like this. Like this. It looks like acetylene. And then aluminum chloride. Aluminum chloride is planar. Hopefully you can all draw the Lewis structure of aluminum chloride by now. And there you go. So the answer is the one that's trigonal pyramidal. Trig pyramidal, so it's not pyramidal. Anyhow, there you go. Number 32, be able to differentiate. Let me make a note on something here. Man, I really cheapers. Okay, number 32. Be able to do what? All kinds of stuff. Differentiate electron behavior in polar covalent versus nonpolar covalent versus ionic bonds. We went over the general concept here that when you have a nonpolar covalent bond, this is when your difference in electronegativity is going to be less than 0.4. If you have something that's ionic, generally your difference in electronegativity between the two elements will be greater than 2. And then if you're somewhere in the range of a delta En of 0.4 to 2.0, then it's going to be polar covalent. All right, there's that. So polar is when we have unequal sharing, right? Like say, for example, and I could give you, lots of examples. If you have a bond between hydrogen and fluorine, right? There's a dipole going this way. If you have a nonpolar covalent, there's equal sharing. Let's say, for example, you have H2, right? There's no dipole there. And then ionic compounds, that's stealing electrons, like the chloride would steal electrons from the sodium to form a cation. Number 33, given a set of molecules, determine which molecule will be polar. Everything that's spherical is going to be nonpolar. So anything that doesn't have lone pairs on the central atom, most of the time is going to be nonpolar. If you've got lone pairs, right, except for square planar, everything is usually going to be polar if it's got lone pairs. And again, it's not a great trick for general chemistry 1, but it will work most of the time. Which molecule has a permanent dipole moment? Well, if you look at aluminum fluoride, AlF3, that does not have a dipole. I'm not going to draw in the lone pairs, but you can see that this is trigonal planar, and there are dipoles going this way, and this way, but they're going to cancel each other out. And so that is a nonpolar molecule. If I draw silicon tetrachloride, right, that's perfectly tetrahedral. All of the dipoles are going to cancel in silicon tetrachloride. If I draw silicon dioxide, that's silicon dioxide. Are there dipoles? Yes. There's a dipole going this way and a dipole going this way, but what do? Starts with C, ends with ancel. That's right, they cancel each other. And if I have selenium oxide, selenium is in group 6A. It's got 6 valence electrons. So when I draw the Lewis structure, I've got a lone pair on the central atom, but then I have 2 double bonds to my oxygens like this. And so this is actually going to have a bent molecular geometry. So it is bent, and therefore there's going to be a resultant dipole. You add these 2 vectors together and you get something like this. And so that is our polar molecule. And you can see it's the only one that has lone pairs on the central atom. So a good trick, again, for most of the time. Given a list of bonds, number 34, determine the bond that is the most polar. All of these bonds are to fluorine. Fluorine is the most electronegative element in the Pauling scale. The elements that it's bound to are germanium. What else do we have? We have sulfur. So germanium and sulfur. We have phosphorus. And we have silicon. So if you look at germanium, silicon, phosphorus, and sulfur, which one of these is the least electronegative? Well, electronegativity decreases when we go from right to left and go down. So the one that's closest to the bottom left-hand side, I guess, if you will, is germanium. And so the least polar here, the most polar bond is going to be the one between germanium and fluorine. Number 35, given a structure, tally up the number of sigma bonds and the number of pi bonds. All right. So I hate these questions. I love organic chemistry, but I don't want to mess something up like this. So I have a pi bond here. So there's 1, 2, 3, 4. So we've got pi bonds. We've got 4. Now, I made a note for myself that I tallied up the sigma bonds. What did I say I got? 32. I hate these problems when they don't have the sigma bond shown, right? Because if you have an OH, there's a sigma bond there, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Shit. Somehow I ended up with an extra bond. Did anybody see where I ended up with my extra bond? There's supposed to be 32. Where did I add an extra bond? I'll let you guys do it. All right, we're going to go with Anthony, who's got 32. I know that that's the right answer. Okay, it's got 32. I'd have to, for some reason, I keep getting 33. I'm adding an extra one somewhere, but whatever. Determine the hybridization of a specific atom. So the carbon with the arrow pointed towards it has 3 regions of electron density. So 3 reds, 3 reds, therefore sp2 hybridized. If I was to point to this one here, for example, could anybody tell me what the hybridization of this one with the red arrow on it? What would the hybridization of that one be? There, I just tallied it up again and I got 32. All right. Okay, so the hybridization, that carbon has 4 bonds, right? That is that methyl, the CH3, 1, 2, 3 hydrogens. Therefore, it's got 4 bonds. Therefore, it is sp3 hybridized. All right, number 37, conceptual understanding of a pi bond. They only happen between unhybridized p orbitals. Remember, if you have 2 p orbitals, like this is a p orbital with an unpaired electron. This is another p orbital with an unpaired electron. If they overlap head to head like that, that forms a sigma bond. However, when p orbitals overlap side to side, like this, and then they share electrons, so you have an unpaired electron and an unpaired electron like that, that's a pi bond. Okay, the side to side overlap, that results in a pi bond. So you need to know the difference between a pi bond and a sigma bond. Given 4 chemical formulas, determine the substance with the highest boiling point. Hint, if it's the one that can hydrogen bond, it's got the highest boiling point. Well, if we look at these molecules, the first one, this is propane, like propane gas. Okay, it's a hydrocarbon. Anytime you have a molecule that has only carbon and hydrogen in it, it is nonpolar, my friend. I don't care if it's got 1,000,000 carbons and 1,000,000 hydrogens, it is nonpolar because there's no polar bonds that can be formed between 2 carbons, and a carbon and a hydrogen is not a polar bond. The next one is butane, like the butane that's found in a butane lighter, which is also a hydrocarbon. So these are both non-polar. They're only going to experience dispersion forces, nothing else. This one and this one both have a capability of hydrogen bonding. So we'll put here, these ones have the capability of hydrogen bonding. However, when you compare these two, you see that this one has a longer chain. And so it's a heavier molecule. It's got more electrons. And so its dispersion forces are going to be stronger. And so the tiebreaker here would be, even though they can both participate in hydrogen bonding, the bigger one is going to have the higher boiling point. There we go. Recognize how a strong electrolyte looks like in water. They look like this. All it means is that a strong electrolyte is going to dissociate completely. So we'll put here strong strong electrolyte equals 100% dissociation. Okay, so you see how everything is broken apart into its particles here. All right, number 40. Given an equation, balance the equation using the smallest set of numbers. So we get zinc hydroxide plus potassium phosphate gives us zinc phosphate and potassium hydroxide. So let's see here. We've got 1 zinc over here, and we've got 3 zincs over here. So we need to at least have a 3 here. We've got 3 potassiums over here. And we've got 3 potassiums over there. That's not going to work, is it? We got 3 potassiums here. We put 3 potassiums over here. So now our potassium is balanced and our zinc is balanced, but our phosphates are not balanced, are they? We got 2 phosphates over here, so we have to have at least a 2 here. So then we have to cancel that out. Now we've got 6 potassiums, so we'll put 6 here. And that works out because now we've got 3 times 2 hydroxides, so we get 6 hydroxides over there. And I think it's balanced. Let's double check. How many? So we got 3 zincs, 3 zincs. We've got 6 potassiums, 6 potassiums. We've got 6 plus 6. So we've got 12 oxygens on this side. And then we've got 3 times 2. So that's 6 plus 6 equals 12 oxygens on this side. We've got 6 hydrogens over here, and we got 6 hydrogens over here. Boom! It is balanced. Okay, so if you're not following exactly what I did here, my thought process, because I'm talking kind of quickly here, what I did was this. So, and this is, I think, a good approach. You know, it's not trial and error. There's rationale to balancing a reaction. Look, I have 1 zinc here and 3 here. So I had to at least have a 3 here. And then I said, well, I've got 3 potassiums here, so I'll put a 3 over there. But then I noticed that I had a big problem because the only place that you see the hydroxide is over here. Okay, and you have 2 of them here times 3. So that would give you 6. Okay, like that. Also, so once you put the 6 in front of this, then you have 6 potassiums and you only have 3 here. So you need to have a 2 there, and now you got it. So now, now it's balanced just like that. All right. What time is it? 6:16. Good grief. Is it 6:16?